Hi there, this is Jacob Nash, and in this video we're going to be looking at some problems for Unit 1 of Physics. Some trickier problems that you might see. Um, and this video is going to mostly cover, your basic kinematics and some vector stuff, and the next video we'll do some other problems, including relative motion. So about this video, um, we're going to be mostly focusing on the longer word problems rather than the easy conceptual questions. At least I say it's easy. Like, for example, the ones that, you know, which graph of the velocity matches up with the displacement. Like, we're not going to be looking at ones like that are more basic. We're going to be looking at ones where you actually have to use equations and numbers and stuff. Um, but those basic concepts are basically embedded within these questions. So another thing is algebra steps are just going to be skipped for time's sake. I'm assuming that you know how to like isolate a variable. That's really the main thing that algebraic thing that you need to know how to do. Obviously, you just subtract or add things to the other side, divide at the end, or whatever you have to do to isolate the variable you need. But I'm not going to show those steps just for time's sake. And also, many of these problems used are created by Pearson Education, so all rights and credit to them. This video isn't profited from in any way. All right. So here are the steps to solving these physics problems. And in fact, if you've ever seen any of my other videos, because I made a lot of physics videos a few years ago, I always said K, N, E, F anyways, but I'm actually going to add in two other letters that are going to be more important for this higher level of physics, which is D and C. So now we have D, C, K, and E, F, and you can remember that by don't call Kyle nearly every Friday. So all those letters, it means draw what the word problem is saying. That's very important. Drawing it is very important because it can give you an easier, it helps you break it down and you can understand what's happening. Then C stands for coordinate system. This one isn't as complex as it might seem. It just is basically here you're just deciding which direction is positive and which direction is negative in the X and Y, which typically it's really just going to be right is positive and up is positive. And then know, you're going to write down what you know, like what they told you in the problem. Sometimes there's some things that are implicitly stated, which you have to be careful about. Um, because you might just think, I don't know, how do I find this? But something they said will tell you how to find something else that you need. And then N, you write what you need to find. Typically, that's just one thing that it's asked. Like, of course, they're just going to ask one thing in the problem, but sometimes you need to find more than one thing. You have to find one thing to find the next. And the way you'll determine that is just by looking at the set of equations you have and figuring out, am I even able to use any of these? And if the answer is no, like if the answer is I can't use any of these equations, then that means you need to find something else first before you can find what they're actually asking. And so technically N and E go hand in hand. They're not really, they're pretty much can be order switched sometimes. And then lastly, find whatever they're asking and just do it. So let's look at this first problem. So a motorist is traveling 20 meters per second. He is 60 meters from a stoplight when he sees it turn yellow. His reaction time before stepping on the brake is 0 0.5 seconds. What steady deceleration while braking will bring him to a stop right at the light? So that's how these problems are going to usually be. It's just going to be some kind of situation, and then it's going to, you know, be something very specific, like, and in this case, it's like what exact steady deceleration will bring him exactly to the stoplight. So even though that sounds super wordy, it's really going to be not that bad. But this one is a little bit more complex just because sometimes there's two different parts of the situation. So there's the part where he's just driving 20 meters per second, and then there's the part as he's slowing down. So there's just really two scenarios in one, but that's not so bad. So we can draw a picture of that. So this picture, you can see we also have done the coordinate system. So we're establishing that x positive is this way, y positive is up. That's almost always going to be what it is. And we can know that the full distance is 60. You're basically just drawing what it says. You have the stoplight, and then there's going to be a certain distance d, as it's said in here, that is going to be as he's slowing down. So let's write what we know. So we know t 20 meters per second. What I mean by that is the time that he's going 20 meters per second is 0.5 seconds because we're saying that his reaction time is 0.5 seconds. So he doesn't slow down yet. So we're saying before he slows down, uh, it, t- uh, it's taking 0.5 seconds. And so the final velocity at the very end of this is going to be zero because obviously he's coming to a stop. And the initial is 20 meters per second. The x full, so the full distance that he's going is 60. That's all we know. That's all that we were told. The things that we need to find, well, we need to find A, acceleration. I really should say AX, but there's really nothing in the y direction right now, but I should say AX. So we need the acceleration that is making him slow down, and we really can also call that deceleration. But the thing is that we'll also need to know X slow down, which means the distance that he's slowing down. Because if we just use the full distance of 60, that's not correct because at first he's not slowing down. So that's what makes this problem a little bit harder. But we need to first find, we don't want 60, we want the distance that he's slowing down. So we'll get to that in a second. We'll just use these kinematic equations. But to find the distance that he slows down, what's going to be the full distance minus the distance that he goes going 20 meters per second. The full distance is 60, and how far does he go when he's going 20 meters per second? Well, all we have to do is multiply 20 times 0.5, so velocity times time, because we know that uh, distance is velocity times time. Um, that's how that goes. Just like velocity is distance over time, when there's a constant velocity, which there is, 20 meters per second at that time. So all we have to do is multiply the times. Another way to think about it is um, if we have seconds times meters over seconds, the seconds cancel out and you're left with just meters. So you know that if you multiply velocity times time, you'll get distance. So the distance that he goes is going to be 10 in the beginning. So that means that the part where he's slowing down is 50, 60 minus 10. Now we can use this kinematic equation, and we have three kinematic equations, if you remember. And this is the one that we'll use just because you choose the one that has what you know. We don't know the time that it takes for him to slow down, so we don't want to use the kinematic equation that has t in it. So we'll use the one that doesn't have t in it, which is this one. So final velocity 0, initial 20, uh, A is what we're trying to find, distance is 50, and um, what do you know? It's negative 4 meters per second squared. And that makes sense that it's negative, because he's slowing, or not because he's slowing down. That's actually incorrect. Because the velocity is positive and we are slowing down. Because of those two things, the acceleration should be negative. Acceleration is whether it's negative or positive is based on um if it's doing the same thing or opposite thing as velocity. So I should not say that because it's slowing down, it's negative. It's actually because the velocity is positive and we're slowing down. So it's because of those two things that it's negative. All right, next problem. That one was definitely a harder one. I don't know. Maybe I shouldn't have started out with that one, but number one is actually one of the hardest ones in this video. This one's going to be actually just kind of flat out weird, because we're not going to actually use any kinematic equations for this one. But this question says ships A and B leave port together. For the next 2 hours, ship A travels 20 miles per hour, 30 degrees west of north, while ship B travels 20 degrees east of north at 25 miles per hour. What is the distance between them after 2 hours? Well, don't we just love some question like this I can already tell if there's angles, we're gonna have some dumb trigonometry, right? Well, it's actually not gonna be so bad. Um, you could use law of cosines actually if you know, but the what we're gonna do is a different way because this is physics and we know things about vectors. So we're gonna use a different method, which pretty much would be easier than the law of cosines anyways. Kind of easier, I guess. But all you have to do is, well, we'll still say what's known. So we know that time is 2 hours. We know that the velocity of ship A is 20 miles per hour. Velocity of ship B is 25 miles per hour. And you know the respective angles, 30 and 20. It doesn't matter that it's not meters per second. I'll tell you that you only have to change it to meters per second when you use the kinematic equations. And the reason why is because any kinematic equation that uses g, the little g, which is 9.8 meters per second squared, anytime you use an equation with g, that's why everything else has to be meters and seconds, because that g has units of meters per second squared. So you can't have differing units. So, but for this situation, we're not going to use g, so it doesn't actually matter that we have miles per hour. Um, so that's what we know. What we need to find is the distance between A and B at 2 hours, which we'll call C. And in this diagram, you can see that we use that distance and we call it C. And so the equations that we use is we'll know that C is going to be A minus B. That's from the vectors. So I actually should put a vector symbol over those. I should have done that. But the vectors, anytime you have two vectors like that are starting at the same point, the distance between them, you can subtract them, and that's actually going to be what it is. That's just a vector rule that you'd want to know. And then secondarily, C is not going to be our answer. C is not actually going to be uh the actual distance. You would have to use this formula that you're going to want to know, which is this is saying the magnitude of C. The magnitude is going to, so we'll have to add two components, the x and y, and take the square root of it. So that sounds complicated, but it's not actually that complicated. So we'll see, how do you do that? So first, we want to know what A and B are. What are the actual distances that both of the ships travel? And you can just do that by multiplying their velocity times time, because I said that already. That's how you can get distance. I'll just actually write that just so you can see, but we know that velocity is distance over time because distance has units of meters and time has units of seconds, and velocity is meters per second. But if you rearrange this equation, and solve for x, you would get x equals vt. So if you multiply velocity times time, you'll get distance. So that's all you had to do. Now, the next thing is the way to get our answer is going to have x and y components separated. So we're going to have to do the x and y components of these. Um, and the thing that you have to be careful with, you might usually think cosine goes with x, sine goes with y. This is probably an important part of the video that you'd want to pay attention to. That is true only if the angle is off of a horizontal line. If your angle is off of a horizontal line, then cosine goes with x and sine goes with y. But this time we have a vertical line. So that means that when you have a vertical line, sine goes with x, cosine goes with y. And if you need proof for that, then you can actually just use trigonometry SOHCAHTOA. But I find it easier to just memorize that. So vertical line, sine x, cosine y. Horizontal line, cosine x, sine y. But we have a vertical line, vertical vertical thing that the angle is off of. If, I don't know, that's not very proper to say, but it's a vertical thing that the angle is off of. So we'll say sine is x, cosine is y, and you can see sine is here, cosine is here, and then you might say I hat, j hat. What is that? Um, if you don't know what that means, we use I hat to represent x components and j hat to represent y components. So the x component of A is right here. It's going to be to find a x component, you do the normal thing, so 40 times it's going to be sine because sine goes with x when it's a vertical line. Sine of the angle, 30. And then why is it negative? Because this is in the negative I hat direction, which just means negative x direction. It's left of the y-axis, so it's negative. The y component is just going to be, once again, you start out with the normal thing. I don't know what else to really say than that. So normal distance multiplied by cosine because it's a vertical line. Cosine goes with y. Cosine of the angle, which is 30, and it's positive because it's over here. In this quadrant, we have negative x, positive y. Then B, you can see same thing. You'll just do the same thing, but you change the value. So 50 sine 20, and both of those are positive because in this quadrant, the x and y are positive. So that we found the components of the vectors A and B now. That's good. Now we will subtract A vector minus B vector to get C vector. So once again, this should really, I'll just go ahead and do it here. These are vectors that we're subtracting. So you can see this part is the A vector minus this, which is the B vector. That's pretty simple. Now, oh, sorry. I thought I almost X'd out the video. Um, now we will rearrange this to where all of the I hat things are beside each other and the J hat things are beside each other. There we go, and that's how I would end up. We would have a sign change, and that's how it would end up. Once again, I'm skipping the algebra because I just assume you know how to do that, but that's not even hard. You just move things over. But now the reason why we did that is because we have to use this formula. Now we have this is the CX, this is the CY. Now, we would calculate those values, negative 37.1, 12.36, square those freaking things, add them, take the square root, and bingo. That's our answer, which is the distance between them. And it's in miles because we start out with miles per hour. So that one was kind of weird. It wasn't really that hard if you think about it. You just had to review, we just had to find out what these values actually were and then find the components of the vectors, subtract the vectors, and then use this formula, and then we found the distance. So that's how you would do a question like that. All right. This is all right. Let's do this one. A car is traveling 15 meters per second and it runs out of gas while traveling up a 25-degree slope. How far up the hill will it coast before starting to roll back down? So the question is asking, what is the distance as it's coasting? How far up indicates distance. So once again, they're not always going to exactly say the thing that you're finding, but how far up that would indicate that we're trying to find distance. So what is the distance that it goes up the freaking thing before it rolls down? Now we will draw a picture, and anytime you have a slope, like or anytime you have an incline or slope, it's usually good to choose. This is why that step C, which is coordinate system, is important. It's not always going to be the same. This is a situation where it's different. You would want X to be against the slope and Y to be up from the slope, not directly up. You see, it's tilted. And the reason why is if you didn't do it tilted, then you would have to have a lot more trigonometric stupid things. But this makes it not that bad if you do it like this. Um, so this is drawn a little bit differently. You could also draw it a different way where the slope is facing the other way. But this person that made this drawing, which I actually didn't do any of these drawings, by the way, in this video, um, but this drawing is chosen that way to show you that yes, you could actually say you could choose that it goes up to the left, which would mean that it's negative 15 meters per second velocity because it's just showing you that you could do it either way. That's the point of this. So we have a left, so we're saying that the negative x direction, so negative 15 meters per second. Because this in the problem is really telling you to speed. This is the velocity because it has a direction. because remember, velocity is a vector, so it has a magnitude and direction. Oh. All right. What do we know? Initial velocity, negative 15 meters per second. I just told you because it's going to the left. You could have done it to the right, and that you would still arrive to the same answer. You just have negatives and positives and certain things different, but you would end up with the same thing if you did the other way. The AX, so the acceleration in the X direction. Right now, we really are not going to care about AY because it's moving in only the X direction because the X direction is this. AX, acceleration in the X direction on an incline is always G sine theta. And um, if you want proof for that, then you would basically break the gravity component, the force of gravity, or not force of gravity component, but you would break the components of the vector and you you would end up getting that, but you don't even really need to know that. All you can just know is that it's G sine theta always for AX. So at least you can know that. It's always that. Um, Angle is 25 degrees. Final velocity is 0 because we're saying how far does it coast before it rolls back down. We don't really care about what happens when it rolls back down. We're saying how far does it coast until it rolls back down. Well, the time interval that we're thinking of is when it's going up until it stops before it rolls back down. So stops. So that's why the final velocity is 0. Need. We need to find the distance that it coasts. Equation that we can use, we'll use this equation because we don't have any information about time, so we don't want to use those equations with the t because then we'll have two unknowns and you can't solve it. In this case, we can use this equation because we know all of these things. We know that the final velocity is 0, initial velocity is 15. Careful, put that negative outside that thing. Because if you squared it, then it would go away. So make it outside of it because we need to make sure that's negative. So careful when you do the calculator. 2 times 9.8 sine 25. That's using this formula, G sine theta. Delta X, you would do your algebra, put that on the other side, subtract that on the other side, or divide that. Um, oh, there's actually a mistake here. Um, the mistake is that this is actually negative 9.8. Sorry about that. Because when you add this to the other side and then divide by it, it needs to be a negative number that you would get this. And so our distance that it goes is negative 27. Now, how come would it be negative? Is because we're going left in this example, so that is considered negative, but it asks for how far would it go up. You wouldn't say negative 27 meters. You'd say negative 27 because it was asking for distance. So that's the answers. That one actually was kind of easy, if you think about it. All right. A lead ball was dropped into a lake from a diving board 5.6 meters above the water. After entering the water, it sinks to the bottom with a constant velocity, and that constant velocity is the one that it hit the water with. The ball reaches the bottom 4.7 seconds after it was released. How deep is the water? Lake, whatever. So you can draw a picture, you can just say, all right, and this is another one of those two-parters pretty much, because there's the part where it's in the air and then the part where it's in the water. And things are different in those two parts. So you can just draw it like that. And what do we know? We know that the change in distance in the air, which I'll just call y air, delta y air, is negative 5.6 meters. Careful. Negative is what it would be because it starts at a higher, see y positive is up. So if we're starting higher and then going lower, that's a negative change in y. So it has to be negative. Careful, because if you don't do that, you get the wrong answer. So negative 5.6 meters. That's supposed to be a delta. Sorry that looks terrible. AY, so the acceleration in the y direction. By the way, we're just talking about something being dropped in only one direction. So this is not projectile motion or launched horizontally. This is just free fall. So we don't care about x anything. AY acceleration is always in free fall negative 9.8 meters per second squared. Initial velocity is 0 because it's not thrown down, it's dropped. If it was thrown down, then there would be a initial velocity, but no initial velocity if it's dropped. Total time in the whole thing, including the air and water, is 4.7 seconds. We need to find the distance that it goes in the lake. So from when it hits the water to the bottom, what is that distance? That's what we're trying to find. Um, the equations that we'll use multiple of the kinematic equations. This one's going to have kind of a lot of parts, but how do we start out? Well, we have to think about it. We're going to have to find multiple things because we don't know that much stuff yet. And if we want to find the distance when it's in the lake, we'll have to find other things first. So we want to find the velocity as it hits the water. Why? Well, for the distance that we're looking for, that velocity is going to be a constant velocity, as it says, and the velocity is the constant velocity that is the one where it hits the water. That's why we want to find that first. But we're going to also want to find the time that it's in the air and the time that it's in the water separately. We know the whole time is 4.7, but we want to know that separately so that we can actually use the kinematic equations. Then we can actually find the distance in the lake. So let's first find the velocity as it hits the water. We can use this equation. Why did I pick this one? Because it doesn't have time. We don't know the separate time for when it's in the air, so we can only use the one that doesn't have time. So you plug in those values, as you can see, that's negative, that's also negative, and the answer is negative 10.5 meters per second. A good technique is to make sure that the answer makes sense. Does it make sense that the velocity is negative? Yes, because velocity is negative when you're going in a negative direction, and down is a negative direction in this case. Now we want to find the time that it's in the air and why. Because if we know the time that it's in the air, then we'll be able to find the time that it's in the water because it'll be the total time minus the time it's in the air. And why do you want to find the time in the water is so that you can find the distance in the water. So we can use this equation, this easy one, to find the time in the air. Plug in those values, it's 1 second. The full, or the time that's in the water is going to be the full time minus the air time, which is going to be 3.7 seconds. Now, if you want to find the or sorry, if you want to find the distance that it's in the lake, well, since it has a constant velocity, we can use one of these basic equations. So you can use these ones like this with the delta anytime that it's a constant velocity, and it is. See? So velocity equals distance over time, or displacement over time, I should really say. Sorry. It equals displacement over time. Displacement equals velocity times time. I've already said that like 2 or 3 times in this video. You can say that it equals VT. So you multiply those two things together. So the change in the displacement is going to be negative 39 meters. But we want how deep is the lake, and you would not use a negative value for that. That's indicating distance. So you take away that negative. So that's something you got to think about too, is like, would we ever report how deep a lake is as negative? No. So that's why we just say 39 meters. All right, next one. A rock is thrown directly upward off the edge of a roof that is of a building that's 66.2 meters tall. The rock misses the building on its way down, and it's observed to strike the ground at 4 seconds after being thrown. No air resistance. So in this chapter and unit, no air resistance because that will make G not 9.8. Um, what speed was it thrown with in the beginning? So this one is not free fall, it's thrown. So um, this one is going to be a little bit, this one's going to actually be pretty easy, but you'll just have to drawing the picture is going to help. But let's first just write what we know. We know that the distance of the building, it's 66.2 meters tall. We know the whole time from when it's thrown until it hits the ground is 4 seconds. We know that the acceleration in the y direction is just g. It always is for um, anything like this in kinematics, and that's always negative 9.8 meters per second squared. We need to find the initial velocity. Equation that we can use is this one right here. Now, why is this one the one that we're going to use? Well, of the three, this is the only one that doesn't have final velocity. And final velocity is not something that we know. It's not going to be zero. Um, it's going to actually be, getting increasing as it goes down in magnitude. And so we don't know what that is. So to, to save time and not have to do more steps, we'll use this kinematic equation that doesn't have final velocity in it. So if you're noticing a trend there, you always use the kinematic equation that um, has the most things that you know. If you have one where you know everything in it, then that's the ideal thing. And that's actually the case here because we know all these things. We know, um, despite the fact that it has an upward distance, see, it goes higher than 66.2 and then goes down. That actually, um, think about it, that distance, you go up, but then you just subtract by it again. So the overall change in distance does not actually matter for that part where it's up. So that doesn't matter. So that's the thing about this problem that might make it tricky. You might think, well, how far does it go up? That actually doesn't matter because it just gets subtracted again from that part. It's like a mirror of it. It cancels out once it gets back to here again. So the only thing that does matter is the time increases, but we know that the whole thing is 4 anyways, so it doesn't matter. So we know everything. So this is actually a really easy one. So you just final distance or sorry, final position, I should say, 0. Initial 66.2. Um we don't know. We're trying to find that. Time 4 seconds. 0.5. You might see this as 1/2 in the equation, by the way, but I just wanted to type that instead. Negative 9.8 and then 4 squared. Never forget your squareds, by the way. Be careful about your squareds and your negatives. Those are the two things that mess people up sometimes. So that was the easy one. Okay. Why is it not going on the next slide? All right. Bob is driving a getaway car after a bank robbery. He's moving 50 meters per second when his headlights reveal a nail strip that the cops placed across the road 150 meters in front of him. If he can stop in time, he can throw his car in reverse and escape. But if he crosses the nail strip, his tires will go flat and he'll be caught. His reaction time before he can hit the brakes is 0.6 seconds. His maximum deceleration is 10 meters per second. Is he in jail? Well, this is just a really stupid question. Well, not really stupid, but as you can see, this is like a whole paragraph. But this could really, there's a lot of information in here that's stupid. So let me just show you. So I'll X out things that are stupid. So, um, we don't care that it's a getaway car. We don't really care it's a bank robbery. We don't care that his headlights reveal a stupid nail strip. We don't care about that. Um, we don't care that he can throw his car in reverse and escape. And we don't care that his tires will go flat. None of this matters for the problem. Um, Anything that I left in there is actually matters. So all we really care about is he's going 50 meters per second. There's something in front of him 150 meters away. Um, and is he going to reach that thing if he decelerates at this rate and has this reaction time? That's all the question is. So it's actually a simple question, but it just has so many stupid things. But it actually is a two-parter like number one. So this is going to be another one where it's like we were going at a constant velocity and then we end up decelerating. So this is actually similar to number one. You can draw a picture. Yeah. And the question saying is he in jail? Really, that's saying, does he reach that spike strip? Yes or no? And what will that actually be represented in equations? We'll see. So what do we know? Initial velocity, 50 meters per second. Final velocity, 0 meters per second. full distance that he goes is 150 meters. Um, time that he's going 50 meters per second for is 0.6 seconds because that's his reaction time. So the time that he's going that speed for 0.6 seconds. Time as he's slowing down, we don't know. Acceleration, so I don't even know why I put that there. Sorry about that. Um, Acceleration as he's slowing down is negative 10 meters per second squared. What do we need? We need to know if the distance that he's slowing down for is greater than the distance that the spike strips away at 0.6 seconds when he starts slowing down. So is this greater? Is this slow down distance greater than this? If it is, then he's in jail. So we will find out these two things because we don't know either of these. So what is um uh basically how far away is the spike strip when you start slowing down? Well, we can find that by um knowing the time. What distance does he travel when he's going 50 meters per second? Well, he's going 50 meters per second for 0.6 seconds. And I've said this already so many times that distance it we can write as velocity times time. So 50 meters per second for 0.6 seconds. He goes 30 meters per second, or sorry, he goes 30 meters in that time. So that means that once he starts slowing down, it will be 150 minus 30. So when he starts slowing down, the spike strip is 120 meters away. So now we can use this equation to find out uh, the distance. And guess what? We use this equation once again because we don't know time. We don't know the time that it takes for him to slow down. So why use an equation that has that? That's pointless. So let's use the equation that doesn't have time in it. So plug in these values because we know all of them. Final velocity 0 because he comes to a stop. 50 is what he started at. Deceleration is negative 10. And so that means that he goes 125 meters in that time when he's slowing down. And since that's greater than 120, that means that he did go over the spike strip and he went 5 meters further than the spike strip. So he's in jail. So that was a question that was like kind of complex. That's the purpose of this video because you'll have ones like that. See, like it really didn't take that long. You didn't have to do that many things. You just had to make sure you understood what it was asking and what information you're given. Uh, okay. Let me erase this stuff. Um, so a rifle was aimed horizontally at a target 50 meters away. The bullet hits the target 2 centimeters below the aim point. What was the bullet's flight time? What was the bullet speed as it left the barrel? So this is really two-parter. So we can draw a picture so we can see, coordinate system is drawn. We can see, oh, the bullet goes down a little bit and it goes over. Okay. What do we know? Initial velocity in the y is 0 because it's launched horizontally. If it's launched horizontally, there is no y component of that velocity that starts out with because it's just exactly in the x direction only at the beginning. Um, Change in x. So what's the distance that it goes in the x direction? 50 meters. What's the distance that it goes in the y direction? I highlighted that because you have to be careful for two reasons. One, it's negative. You'd have to know it's negative because it goes down. And then the other thing is that we had centimeters here. You have to convert that to meters. And why? Because we're using this, well, actually, because we have meters here, that's the real reason. These units have to match up. And also because we're using G and G needs meters and seconds. So G acceleration in the Y, AY is negative 9.8 meters per second squared, as always. We need to find the t, so the time that it travels. And we need to also find the initial x velocity. Solving, let's use this equation. Now, again, why would we use this equation of the three kinematic equations? Because this is the one that doesn't have final velocity in it. We don't know its final velocity, so let's use the one that doesn't have that. You might say, oh, well, this is going to be hard to find time because I see t here and here. Oh no, I'm going to have to do some horrible, you know, quadratic formula or something. You might think that at first glance, but what's this thing that's red? It's zero. See? So that whole section just cancels out this part. So bye-bye to that. We don't That's the thing that's nice. It's like since that's zero, this part cancels out, so you don't have to worry about solving for two t's. So now it's just this. So initial y position is zero. You plug in that, make sure it's negative, and then of course you'd have to remember to take the square root at the end to get your answer. And that's the time. Um, that's actually a really quick time, but this is a rifle, so that makes sense. So it's good to do that. Think about if it makes sense. So now initial x velocity, this is going to be a similar thing where like once again, you might be like, oh, I don't know something. Well, the ax, that's red because that's zero. So we don't when something's launched horizontally, the ax, so acceleration in the x direction is always zero. So bye-bye to that whole thing. So it actually becomes just this equation. And again, we use this equation because we don't know the final velocity. So this is the kinematic equation that doesn't have v final. So you plug in these values and solve for VOX, or initial x velocity, and that's 782 meters per second. Does that make sense? Yeah, it does, because it's a rifle, so it should be a very fast velocity. So that one, once again, is not a hard question at all, but you just would have to know, oh yeah, that's zero in this situation. That's zero. It would cancel out, whatever. You have to know those little things. All right, last question that we will do in this video. A tennis player hits a ball 2 meters above the ground. The ball leaves the racket at a speed of 20 meters per second at an angle 5 degrees above the horizontal. The horizontal distance to the net is 7 meters, and the net is 1 meter high. Does it clear the net? If so, by how much? How much does it miss? Or if not, how much does it miss? So, what is this question asking? It's not super clear at first. Like, does it clear the net? Once again, just like how the one, is he in jail? It's like a yes or no question, but it's saying if so, by how much. So really, we're just saying, is the position of the ball higher than the net, which is 1 meter, when it's at the position of the net? So is it higher than 1 meter? Yes or no? That's what the question is. Oh, for some reason that's already on there, so I don't know why. Sorry about that. So what do we know? We know that the initial y position is 2 meters. Initial x is zero. Initial velocity is 20 meters per second. You gotta be careful. That's actually just the general direction. So that's not X or Y. This is hit or launched, if you want to say. This is considered projectile motion because it's launched in an X and Y direction. So this is not just one direction or the other. It's just in between, or not really in between. It's like obviously 5 degree only, but you can use trigonometry to find the components, as we know. The angle is 5 degrees. Final X position is 7 meters. The final Y position is what we need to know, but the X, or the net, where the net is 1 meter, and we just need to know what the final Y position is, and is it higher than 1? That's what we're trying to do. So as you can see, that's what we need to find. So let's find the components of the initial velocity. What you do is you multiply the initial velocity times either cosine or sine, and in a situation like this, um, you have to think about, remember way earlier in the video, I said it's based off of what the angle is against. The angle is against a horizontal line. So if the angle is against a horizontal line, then cosine goes with x, sine goes with y. Remember the other example where we had the ships going north, then it was against the angle was against a vertical line, so it was switched. But we're against a horizontal line, so cosine goes with x, sine goes with y. Again, if you wanted to confirm that, you could look at SOHCAHTOA, but I find it easier to just remember that if you kind of sucked at trigonometry like I did. So now you can see cosine goes with x, sine goes with y, and do these answers make sense? Yes, it makes sense that there's a way higher initial x velocity because the angle is hardly anything. So it's pretty much only going in the horizontal direction. So it makes sense that the initial x is way higher. So now let's use a kinematic equation to find final y. We will use this. Why? You always ask, why would I use this equation? Because we don't know final velocity. So we'll use the equation that doesn't have final velocity. So basically, all of the equations always have distance in them, displacement. All of them always have initial velocity. All of them have acceleration in them. But one of the equations doesn't have time and one of them doesn't have final velocity. So that's what you should ask yourself when you're choosing between the equations, kinematic equations, is do I not know time? Then use the one that doesn't have time. Do I not know final velocity? Then use the one that doesn't have final velocity. If there's something else that we don't know, like acceleration or distance or something, then you might have to do an alternate extra step. But that's the good way to think about it. But this, as I'm plugging in the values, you might actually be saying, well, I don't know time either. And that's actually what I just said a few seconds ago. What if you don't know either of them? Now, well, all the equations have time, or not all the equations have time, but all of them have either final velocity or time, but we don't know either. We don't know the final velocity or the time, but it's actually easy to calculate the time because the time in the y direction is going to just be um, distance over velocity. That goes once again from this equation, which is velocity equals distance over time, and we're in the y direction, so I'll just say y over t. If you wanted to solve for t, t would give us y over v. Rearranging that equation, t equals y over v. And so how are we able to use this? Because you can only use this equation when we have a constant velocity. Well, um, we actually are going to be having a constant velocity um, in this situation. So that's why that we're not going to have a constant y velocity, but we can use this in a situation where you have a projectile like this, you're able to use this formula for the y direction. And so that's just what you can just know. So the velocity is changing as we go, but um we can actually use this formula y or t equals y over v. Um so oh wait, never mind. I'm sorry. I don't know what I was thinking. So we actually this is the x distance. So that's what I was thinking. So the y velocity is not constant, but the x velocity is. I'm sorry about that. So that I should have mentioned that. So launched horizontally or launched at an angle, projectile, we have constant velocity, which is why we had in the last problem acceleration in the x is 0. So that's the reason why we can use this. So I'm sorry, this is actually x that we're doing. So t equals x over v. We could not use y over v. And for one thing, we don't even know that anyways. So we could not use that. Um, But you can only use this formula if the velocity is constant and the velocity in the x direction is constant. So we are able to use this to find time. So that's what makes this one a little bit tricky. But if you notice, these kinematic equations can be used and we can change it to x or y. But what is the same between all of them is time. Time doesn't change if you're in the x or y direction. So they connect through time. So that is why you're able to use this. So sorry about that little mess up there. I was not thinking correctly about my reasoning, but that's how we find time. So is that since velocity is constant in the x direction, we were able to know that it's just going to be the distance divided by velocity using this equation. And so 7 divided by 19.92, and you plug that in there, you know everything else, and then the answer is 2.0075, and that is higher than 1. So that means yes, it clears the net, and by how much? 1.0075 meters. So that's going to be it for this video. Um, and I'm going to have a part two of more questions because we didn't do any relative motion. So we're going to do that and some more in the next video. So thank you for watching.